This video will go over Carlos Reyes's book, RCAdvisor's Model Airplane Design Made Easy. It will cover chapters 1 through 5. Chapter 7 is over power systems. Chapter 8 is about the overall design process and will be covered in another video. Fluid dynamics. Lift. Lift is produced from the higher pressure below the wings and lower pressure above the wings. The pressure differential is created by shaping the airfoil and angling the wings down. Drag. Drag can be broken down into three main types: skin, form, and induced drag. Skin drag comes from the friction of the air scraping against the body of the plane as the plane moves forward. Form drag is the force coming from the object bumping against an adverse pressure gradient. Think of it as the drag from the front of the plane hitting against the air at speed. Induced drag is the component of the lift force aiming backwards compared to the plane's velocity. This is a necessary component while producing lift. Parasitic drag is a term for the combination or total of form drag, skin friction, and interference drag. Viscosity is a measure of the resistance of a fluid to deformation. Viscosity comes from the atoms of the fluid having an intermolecular attraction to each other. Laminar versus turbulent flow. Laminar flow describes the motion of a fluid flowing smoothly across a surface. Laminar flow produces little drag, high lift, and is easier to calculate. Turbulent flow describes motion of a fluid in chaotic or spiral paths. This turbulent flow produces high drag, little lift, and is very hard to calculate. Turbulent flow happens when air separates from the airfoil. Reynolds numbers. When analyzing any fluid circumstance, the Reynolds number is a ratio of internal force to viscous forces. For airfoils, the Reynolds number can be thought of as the ratio of the airfoil's area to its perimeter. When the airfoil is made larger, the Reynolds number increases. Airfoils. Lift and drag coefficients. Lift and drag coefficients work according to these equations: L equals lift, A equals area, V equals airspeed, or the velocity of the air relative to the plane, meaning wind must be taken into account. P, or in actuality rho, is the density of the air. D equals induced drag. CL is the coefficient of lift. CD is the coefficient of drag. You can find these numbers for almost any airfoil on airfoiltools.com. Here are the author's recommendations regarding airfoils. Airfoils should be no more than 6% thick, have 5% or less of camber, and have maximum thickness at 25% of chord. A camber of 3% gives the best lift-drag ratio. A camber of 5% gives the best maximum lift. A normal airfoil is dangerous if the center of gravity is moved beyond 33% of chord. Propellers. Diameter and pitch calculation. A common designation is 12 by 6, meaning the propeller has a diameter of 12 inches and a pitch of 6 inches. Propulsive thrust. Propulsive thrust is the forward force the motor and propeller produce that balances out the drag. When the total drag force and propulsive thrust are equal, the plane no longer accelerates. If this happens at max thrust, the velocity is called cruising velocity. Efficiency. The larger the diameter of the propeller, the more efficient it will be. This is because power from the engine is constant and the RPM can drop. Efficiency goes down as airspeed increases. Advance ratio. The efficiency of the propeller will be the same at the same advance ratio. Advance ratio equals airspeed over rotations per second times propeller diameter. Equation 3.1. A propeller blade normally operates at a Reynolds number of 100,000 to 400,000. Structures. Table 4.2 shows the tensile strength, compressive strength, and modulus of elasticity for many common building materials. The tensile strength is the maximum pressure the substance can withstand in tension. The compressive strength is the maximum pressure the substance can withstand when being compressed. The modulus of elasticity describes how much pressure the substance takes to stretch a certain fraction. Table 4.3 shows the bending moment and shear load percentages at various positions along the span of the wings. This is important when considering how to design the inner wing structure. Bending moment can be seen in this example graph in XFLR5. Bending moment is equal to wingspan over 4 times maximum load. Wings. Aspect ratio describes the ratio of the wingspan to the length from the leading edge to the trailing edge. For tapered wings, it can be calculated as wingspan squared over wing area. Sweeping a wing increases the apparent chord size. 10 degrees of sweep is roughly equivalent to 1 degree of dihedral. Sweeping a wing decreases max lift. Table 5.1 shows the rate of lift loss with increasing sweep angle. Winglets are extensions to the wings at far more extreme dihedral angles. Winglets prevent wingtip vortices, minimizing the effects of induced angle. However, the winglets themselves produce drag, therefore they should only be used on very low aspect ratio designs. Scale effects. Planes cannot be designed by simply shrinking or expanding existing models. Weight and thrust increase with the cube of the scale factor n. Wingspan and wing loading increase linearly. Power needs to increase by n to the power of 3.5, and airspeed increases with the square root of n. That is all for this video on RCAdvisor's model airplane design. Chapter 8's overall design process will be covered in another video.